now we get to see some examples of topologies that are still pretty weird, but not entirely pathological like the discrete and indiscrete topologies were. These are a bit more normal, but still weird enough to make them worth talking about. In particular, you could define, given some set X, a topology where the open sets, using the letter U for open, because I don't like using capital O, tends to look like a 0. So the only open sets are those sets whose complement is finite. That ends up being a topology. I encourage you to verify it by yourself. It uses some knowledge from set theory and what it means to be, well, cardinality and stuff like that. But this topology is called the cofinite topology on the set X. Cofinite, meaning complement is finite. And finite referring to the cardinality of that complement. Okay, so that does turn out to be a topology. The empty set has to be included in here. So let me actually scoot this over and I'll add that in. Right, because the empty set might not be one of these sets, unless X were finite itself, but let's add it in just to be sure. So if you have the empty set tossed into that collection tau, then you do get the A topology, and you call it the cofinite topology. And you can verify it's a topology because, okay, the complement of the whole space would be empty, and the empty set's certainly finite. The complement of, let's say you have two open sets, two sets whose complements are finite, then to check that their intersection is cofinite, you would take the complement of the intersection, apply De Morgan's laws, and it kind of falls into place. And same story for unions. If you started with an arbitrary collection of cofinite sets, then their union will be cofinite, because if you take the complement of a union, you get the intersection of the complements, and if all those complements are finite, the intersection will also be finite. So anyway, that's how you check it's a topology. And if you want to get even weirder, you can talk about the cocountable topology, which is defined right below it, where you say that a set is open if its complement is countable. And again, I should be careful and just toss in the empty set here in the event where my whole space isn't necessarily countable, then we want to be careful. But this is called cocountable. Same story, co standing for complement. So complement is countable. And very similar story there. Okay. These are pretty weird to wrap your head around. So for examples, I'm just going to show you examples of subsets that are cofinite or cocountable. But first, I'm going to mention if you have some finite set that you're working with, if X is finite, then the cofinite and cocountable topologies actually end up just giving you the discrete topology. Think through why that might be for a second. The answer is that if you start with a finite set, no matter what subset you take, its complement will also be finite. Right? Every possible subset is finite, so all complements are finite, and also all complements are countable. Right? You're not going to get some infinite set or some uncountable set if your entire universe is already finite. So yeah, every complement is finite, every complement is countable. That means every set is open, which means you get the discrete topology. So it's really only interesting to talk about the cofinite and cocountable topologies if you have infinite sets. In particular, what if we take the integers? So x equals boldface z, the integers. What kind of subsets could we take that are cofinite or cocountable? Well, if you took this set, the set of all points in x, so the set of all integers whose absolute value is greater than 1, well, we could draw that, I suppose. 0, here's 1, -1, 2, -2, so on and so forth. And the only points who are going to have absolute value greater than 1 are those points that are outside of, well, let me just add a couple more points here. For example, 2 and 3 and 4 and so forth. -2, -3, -4, and so forth. So that would be my set A. A is in purple. And that turns out to be cofinite. Why? Well, its complement, we'll use red for complement. Its complement just has 3 points. So its complement is finite. That means A is a cofinite set. Or in other words, it's an open set in the cofinite topology. It's also cocountable, right? Any set that is cofinite is automatically going to be cocountable. If your complement's finite, well, everything finite is countable. Okay. You could, of course, also take something like this. Take the integers and subtract the points 1, 2, and 3. The complement of that is just going to be 1, 2, and 3, which is finite and countable. So kind of similar story. How about this, though? What if you took the natural numbers? So again, here's my number line. -3, -2, -1, 0, 1, 2, and 3. And I'm saying that depends on how you define the naturals, but let's say we define it to be the positive integers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, go on forever. That's our set A. Then our complement is going to be all of the negative integers, as well as 0. Complement. And A complement is not finite. Right? So A is not a cofinite set because its complement is not finite. It is, however, cocountable. Right? The red dots I drew there do form a countable set, which you should know from your set theory course. And you can use this logic to show that actually every set is cocountable if the space you're working in is the integers, or more generally, if the space you're working in is countable to start with, then every set is countable, meaning every set's complement is countable, meaning every subset is open. So again, you get a weird case. Here we have, some things being cofinite and some not. But if your set is countable, then the co-countable topology is the discrete topology. So that means to get something really interesting, we have to proceed to where my space is uncountable to begin with. And in that case, yes, you can get all sorts of weird things happening. So R minus the point 0 is both cofinite and cocountable. The complement is just the point 0. That's a finite set, and it's a countable set. R minus the integers. Let's say we drew that. R minus the integers means you're taking everything except for the integers. So sort of all the intervals between integers. That's your set A. And that means their complement is the set of integers, right? But we know the integers are countable. They're not finite. Okay, so this set A is not a cofinite set, but it is co-countable because the red set is countable. The complement is countable. So then the question is, can you come up with something that's neither cofinite nor co-countable? And the answer is sure. If you again took the real line, say 0 is here, and then say, just take the positive real numbers. So that's your set A. Well, to figure out if it's cofinite or co-countable, you want to take its complement. But its complement is going to be neither finite nor countable. So you would say this set A is not an open set in either the cofinite or co-countable topologies. Right, that was kind of fast. Really, the cofinite and co-countable topologies are another place where we get a lot of counterexamples. They're not used super frequently for their own sake. And so also, I mean, they're not very intuitive, but it's good to see their definition and figure out what it really means for a set to be open in either of those topologies. Thanks for watching.